तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Welcome back to Prestressed Concrete Structures. This is the first lecture on Module 8 on cantilever and continuous beams. First, we shall have an introduction on cantilever beams. Then we shall move on to the analysis of cantilevers, then determination of limiting zone, and finally we shall cover cable profile. Prestressed cantilever beams are present in buildings and bridges. Usually, the cantilever is provided with a back span, which is also called anchor span, to reduce the torsion in the supporting member. In a building, the cantilever can be an extension of a continuous beam. In a bridge, the cantilever is a part of the balanced cantilever girder. We shall see that the cantilever is a part of an beam. In a building, it can have a back span. Like in this figure, the cantilever on the right has a back span which reduces the moment in the supporting column. Also, the cantilever can be a part of a continuous beam. That means usually we do not find cantilever by itself, we find either with a back span or as a part of a continuous. A cantilever is a part of a balanced cantilever girder. This is a photograph during the construction of the Pamban bridge at Rameswaram in Tamil Nadu. Here you can see that on each pier there is a balanced cantilever girder, in the sense that there is a cantilever on each side, so that the eccentric load on the pier is reduced, and the cantilever on the two sides is made in a progressive fashion so as to have minimal effect of eccentric load on the piers. The important aspect of the design of prestressed cantilever is the selection of cable profile. The cable profile refers to the profile of the CGS, which is the variation of the distance of the CGS from CGC along the length of the beam. When we discussed simply supported beams, we had talked about the cable profile. That means once we have done the analysis for the critical section, we find out the eccentricity at the critical section, and then we determine the cable profile along the length of the beam. The essential difference between the analysis of a simply supported beam and a cantilever is in the selection of the cable profile, and for a cantilever it is different than that of a simply supported beam. The analysis of a section at a particular location of a prestressed cantilever is similar to that for a simply supported beam. The difference is that for gravity loads, the bending moment in cantilever is negative, that is, compression is generated at the bottom of the beam. Thus, the CGS is placed above the CGC for that particular location. Whatever we have studied for a simply supported beam, the analysis or the design is applicable for a cantilever beam as well. But the difference is that for a simply supported beam, the moment is always positive. That means compression is created at the top due to bending. But for cantilever beams, due to gravity loads, the moment is negative. That means compression is created at the bottom and tension is created at the top. The equations that we have used for a simply supported beam can be used for a cantilever, provided we take account of the sign of the moment and then we place the CGC, the CGS above CGC because the moment is negative. This is the essential difference in the design of a cantilever beam with respect to that of a simply supported beam. The following aspects need to be considered in the analysis and design of a prestressed cantilever beam. First, certain portions of the backspan are subjected to both positive and negative moments. Hence, there will be two design moments at service loads. In a simply supported beam, we had seen that throughout the length of the beam is always subjected to a positive moment due to gravity loads. But in a backspan of a cantilever beam, the same section can be subjected to a positive moment or a negative moment depending on the loading condition. Thus, we have two values of design moments for most of the backspan under service loads. The second aspect is the beam may be subjected to partial loading and point loading. A cantilever beam, if it is subjected to a partial loading or a point loading, can generate a different type of moment condition as compared to when the load is distributed throughout. Hence, a partial loading or a point loading analysis becomes important for a cantilever. The third important aspect is the sequence of loading is important to design the prestressing force. During construction, the sequence of loading in a cantilever is important to design the prestressing force, and the prestressing force can be applied in stages to take account of the sequence in the loading. The fourth important aspect is high values of moment and shear occur simultaneously near the support. For a simply supported beam, the midspan is usually the location of maximum flexure, and a section close to the support is the critical section for shear. But in a cantilever beam, the sections near the supports can be critical both for shear and moment. Hence, the sections near the supports have a larger depth compared to the sections away from the support, and this variation of the depth along the length of the beam should also be considered in the analysis. Next, we are studying the important aspects of the analysis of a cantilever beam. The analysis of a cantilever beam with a backspan is illustrated to highlight the aspects stated earlier. The bending moment diagrams for the following load cases are shown schematically in the following figures. First, we shall see the bending moment due to the dead load. Next, we shall see the bending moment due to live load only on the backspan. Third, we shall see the live load only on the cantilever span and what is the bending moment due to that. And finally, we shall see the envelope moment diagrams. This is a sketch of a cantilever on the right side and a backspan on the left side, and the dead load is throughout the length of the member. It need not be uniform if the depth of the member is varying, but for the sake of convenience, right now we are showing it as a uniform load. Due to the dead load, the moment in the cantilever is negative with 0 at the end and with increasing value towards the support. When we go to the backspan, then we observe that close to the support we have negative moments, and then as we move away from the support and proceed towards the left, we can have positive moment in the backspan. This is the moment diagram due to dead load which occurs throughout the length of the beam. In the second figure, we are having the live load only on the backspan, and due to the live load, the backspan experiences a positive moment, and depending on the magnitude of the live load, the location of the maximum moment can be anywhere in the middle of the backspan. Here, for convenience, we have shown a uniform live load throughout the backspan, and observe that throughout the backspan the moment is positive. Third, the live load is placed only on the cantilever span, and here we find that the cantilever is subjected to a negative moment which increases from the 0 value at the end towards the support, and then in the backspan the moment varies linearly from the support at the right to the support at the left, where the moment drops down to 0. If we have the dead load and the live load acting throughout the length of the beam, then we have a combined moment diagram where the cantilever has a high negative moment, and then as we enter the backspan we have negative moment near the support and a positive moment towards the left support. Now, from this diagrams, that means we have the live load on the backspan, or the live load in the cantilever span, or the live load throughout. From this different placement of the live load, we develop the envelope moment diagrams for the total beam. In this figure, we are seeing the envelope moment diagrams. The orange line is the maximum moment in an algebraic sense. We see that in the backspan we do have high positive moments towards the left support, and then as we are coming towards the support on the right, we will not observe any positive moment, but the value of the negative moment can be less under certain loading conditions. And in the cantilever, the M max value is always negative depending on the load distribution on the beam. If we are taking the M min, which is the minimum value in an algebraic sense, that in that case we find that the moment in the cantilever is substantially high close to the support, and then in the backspan as we move from right to left, the moment drops down. There may be a region where there is no negative moment generated, which is close to the left support, but otherwise most of the backspan has a negative moment which is given by the envelope diagram of M min. notice that certain portions of the backspan can be subjected to both a negative moment and a positive moment depending on the load conditions. If I pick up a section somewhere at the middle of the backspan, we observe that M max is positive and M min is negative. Since the two envelope values have opposite sign, that means that particular location will experience both positive moment and negative moment under the service loads. In the envelope moment diagrams, M max and M min represent the highest and lowest values. These are algebraic values with sign of the moments at a section respectively. Thus, M max is the maximum value in an algebraic sense, M min is the minimum value at the algebraic sense. Why we are saying it is algebraic is that if we are not comparing the numeric value of these two yet, we are considering these two moments with their respective signs. Note that certain portions of the beam are subjected to both positive and negative moments. This is an important aspect of a cantilever beam with a backspan, that there are locations in the backspan which is subjected to a positive or a negative moment under the service loads. For moving point loads, as in bridges, first the influence line diagram is drawn. The influence line diagram shows the variation of the moment or shear for a particular location in the girder due to the variation of the position of a unit point load. The concept of influence line diagram is covered in a structural analysis course. In this particular topic, we are not covering influence line diagram, but we are briefly mentioning that the influence line diagram is used if there is a moving point load. The influence line diagram shows the variation of moment or shear at a particular location due to the variation of the position of a unit load along the length of the beam. Now, once the influence line is first developed, then the vehicle load is placed based on the influence line diagram to get the worst effect. Thus, in bridges, the effect of live load is designed based on influence line diagram, where once the influence line diagrams are available, then the vehicle load is placed in such a way so that we get the worst effect, whether it is the positive moment or whether it is a negative moment or whether it is the shear. Depending on each of these variables, from the corresponding influence line diagrams, we can place the load for the worst condition. Next, we are moving on to the determination of limiting zone, which is done after the analysis of the beam. The limiting zone of placing the CGS of the tendons is helpful in selecting a cable profile. I said earlier that once the analysis of a cantilever is performed, the sectional analysis or design is very similar to the simply supported beam. But the difference is, since the moment has different sign and the sign of the moment can change based on the location of the beam, selecting an appropriate cable profile is important in the design of a cantilever beam. To have a proper cable profile, first the limiting zone is determined, and here we shall recollect the concept of limiting zone. The limiting zone was explained for a simply supported beam under design of members for flexure. Here the concept and the equations are first reviewed for a simply supported beam with positive moment. That means we shall first check how did we develop the equations for a simply supported beam. The same equations can be used for a cantilever beam, provided we are particular about the sign of the moment, and then we can determine the limiting zone of placing the CGS of the tendons in the cantilever beam. There are three types of prestressed members as per our code. For a fully prestressed member, which is referred to as type 1, tension is not allowed under service conditions. If tension is also not allowed at transfer, the compression in concrete, which will be referred to as C, always lies within the current zone. The limiting zone is defined as the zone for placing the CGS of the tendons, such that C always lies within the current zone. Also, the maximum compressive stresses at transfer and service should be within the allowable values. That is, how do we determine the limiting zone for a simply supported beam? That for a simply supported beam under positive moment, we find out the extreme positions of C that is possible without creating any tension for a type 1 member. The minimum moment is at transfer, and at that time C can push down to the lowest current point, and the maximum moment is under service loads, where C can be shifted to the upper current point. This maximum travel of the C is helpful to have an economical section. Now, since we are not allowing any tension in the section, the C always lies within the current zone of the section, and this determines the limiting zone of a simply supported beam. Let us now check what are the equations to find out the limiting zone. For limited prestressed members like type 2 and type 3, tension is allowed at transfer and under service conditions. The limiting zone is defined as the zone for placing the CGS such that the tensile stresses in the extreme edges are within the allowable values. Also, the maximum compressive stresses at transfer and service should be within the allowable values. The difference of determination of the limiting zone for type 2 and type 3 members as compared to a type 1 member is that in type 2 and type 3 we allow tensile stresses at transfer as well as under service, and based on the allowable stresses we find expressions of the limiting zone where we place the CGS in such a way that C may lie outside the current zone, provided that the tensile stresses in the opposite phase is within the allowable value. Also, the compressive stresses should be within the allowable values both at transfer and at service. The limiting zone is determined from the maximum or minimum eccentricities of the CGS along the beam corresponding to the extreme positions of C. Thus, once we know the extreme positions of C, we can determine the corresponding maximum and minimum eccentricities of the CGS at a particular section, and when we draw the loci of this maximum and the minimum positions along the length of the beam, we determine the limiting zone. Remember that the limiting zone is related with the CGS of the tendons. Individual tendons may lie outside the limiting zone. That is, when we are talking of limiting zone, we are talking about the placement of the CGS within the limiting zone. Individual tendons may lie outside the limiting zone provided the CGS is lying within the limiting zone. For a simply supported beam, the maximum eccentricity, which will be referred to as E max, at any section corresponds to the lowest possible location of C at transfer. This generates allowable tensile stress at the top of the section. Thus, the maximum eccentricity Emax is determined corresponding to the lowest position of C at transfer. The maximum compressive stress at the bottom should also be within the allowable value. The minimum eccentricity, which is represented as E min at any section, corresponds to the highest possible location of C at service that generates allowable tensile stress at the bottom of the section. Thus, the minimum eccentricity of the CGS is calculated from the highest position of the C under service loads, and this will generate allowable tensile stress at the bottom of the section. The maximum compressive stress at the top should also be checked to be within the allowable value. The values of Emax and Emin can be determined by equating the stresses at the edges of concrete within the allowable values, else explicit expressions of Emax and Emin can be developed. Thus, in order to determine the limiting zone, we can calculate Emax and Emin for a particular beam for the given loading conditions, or else we can try to determine them from some explicit expressions which are discussed here. These expressions help us to determine the maximum and minimum eccentricities at several locations along the length of the beam. The following material gives the expressions of Emax and Emin for type 1 and type 2 sections. The values of Emax and Emin can be determined at regular intervals along the length of the beam, from which we shall determine the limiting zone. The zone between the loci of Emax and Emin is the limiting zone of the section for placing the CGS. Here we shall recapitulate the expressions of Emax and Emin for type 1 and type 2 members. For type 3 members, the expressions are similar to the expressions of type 2 members, the only difference being the value of the allowable tensile stress. Now, once we have determined Emax and Emin at regular intervals along the length of the beam, then we have the limiting zone, which is in between the loci of Emax and Emin along the length of the beam. To have the analytical expression, we are first seeing a type 1 section at transfer. The lowest possible location of C is at the bottom current point. The tension T is at the level of the CGS. The stress at the top is 0 for a type 1 section at transfer, and the stress at the bottom is FB. KT and KB represent the current distances or the distances of the current points from the CGC. CT and CB represents the distances of the top and the bottom fiber from the CGC, and Emax is the distance of the CGS from the CGC when C lies at the bottom current point. We are using this stress diagram to develop the expression of Emax. Emax minus KB, which is the lever arm by which C has shifted from T, is equal to the self-weight moment that is acting at transfer divided by the pre-stress at transfer, which is denoted as P0. Transposing KB towards the right side, we have Emax equal to MSW divided by P0 plus Kb. Thus, this is the expression of Emax for a simply supported beam for the load condition at transfer, where we have the moment due to the self-wet, the prestressing P0 and the geometric property Kb. Using these expressions, we can calculate the value of Emax at a particular location. Of course, we have to check that the stress at the bottom should be less than the allowable compressive stress at transfer. Next, we are determining E min for type 1 section under service loads. Under service loads, we are allowing C to traverse as high as possible, so that it is at the top current point under service loads, for which the stress at the bottom is 0 and the stress at the top is represented as Ft. The location of the CGS for the uppermost location of C is the E min, or the minimum possible eccentricity. From the stress diagram, we can find that the lever arm through which C has shifted, which is E min plus Kt, this is equal to the moment under service loads, which is represented as Mt, divided by the effective pre-stress at service, which is denoted as Pe. Transposing the term Kt on the right side, we have an explicit expression of E min equal to Mt divided by Pe minus Kt. Thus, given the values of Mt, Pe and the geometric variable Kt, we can determine E min at a particular location. Of course, we need to check that the stress at the top is less than the allowable compressive stress under service loads. If for a particular section E minimum comes out to be negative, it implies that the CGS can be placed above CGC. This happens near the supports of a simply supported beam. Next, we are recollecting the expressions of Emax and E min for type 2 section. At transfer, there is allowable tensile stress at the top. The position of C is outside the current region by a distance E1, and the lever arm between C and T is represented as E2. Emax is the position of the CGS such that C is in the bottommost location, which creates allowable tensile stress at the top during transfer. The lever arm by which the C traverses is Emax minus Kb, which is equal to MSW plus FCT allowable times A times Kb divided by P0. This expression is a general form of the expression that we have seen for the type 1 member. Transposing the term of Kb on the right side, we have Emax equal to MSW, which is the moment due to self-wet, plus FCT allowable, which is the allowable tensile stress in the concrete at transfer, times the area of the section times Kb whole divided by P0 plus Kb. Thus, this expression is applicable both for type 2 and type 3 members with the appropriate value of FCT allowable. Note that if FCT allowable is made 0, then this expression becomes same as that for a type 1 member. Thus, this expression is more generic as compared to the expression for a type 1 member. Also, we have to check that the stress at the bottom Fp is less than the allowable compressive stress at transfer. For service conditions, C is at the maximum level, which can be beyond the current point, and here the distance of C from the upper current point is denoted as E3. The corresponding location of CGS is E min, and the stress at the top is represented as Ft, and the stress at the bottom is the allowable tensile stress in the concrete under service conditions. With this stress block, we can write the expression of E minimum plus Kt, which is equal to Mt minus Fct allowable times A times Kt divided by Pe. Transposing the term of Kt on the right side, we have E minimum is equal to Mt minus Fct allowable times A times Kt divided by Pe minus Kt. Thus, this is an explicit expression of E minimum corresponding to a type 2 section under service load conditions. The same expression can be used for a type 3 member if we have the appropriate value of Fct allowable. Note that this expression is a more generic form of the expression for a type 1 section, because once we substitute Fct allowable equal to 0, we find that this expression becomes same as the expression for a type 1 section. Also, we need to check that the stress at the top should be less than the allowable compressive stress under service conditions. With this recapitulation of the determination of limiting zone for a simply supported beam, we are moving on to the determination of limiting zone for a cantilever beam. In a simply supported beam, the external moments are always positive. The minimum moment is due to self-weight, the maximum moment is under service loads. For cantilever beams, the minimum external moment need not be at transfer when the moment is due to self-weight. That means when we are trying to determine the limiting zone for a cantilever, we have to be careful that the minimum moment may not be at transfer. The moment at transfer is due to self-weight only. We have to also check the moment conditions under service loads. Under service loads, there are two moments, M min and M max at a location, which are obtained from the envelope moment diagrams. Unlike a simply supported beam, where we have only one value of the moment under service conditions, in a cantilever beam, we can have two moments, M max and M min. If they are of opposite sign, then we have to consider both the values, and this is the essential difference between the analysis of a cantilever beam with respect to that of a simply supported beam. Thus, we have three moment values at a particular location. One is due to the self-weight, and another is from the envelope moment diagrams under service loads, which give M min and M max. The maximum and minimum eccentricities E max and E min at a particular location are first determined for service loads from M min and M max respectively at that location and the effective prestress Pe. That means first E max is calculated at a particular location from M min, which is obtained from the envelope moment diagram. E min is calculated from M max at the particular location. Both E max and E min we are calculating first for the service loads, and then we are checking for the transfer condition, that we calculate another set of Emax and Emin for the load at transfer from the self-weight moment MSW and the prestress at transfer, which is P0. The final Emax is the lower of the two values calculated at service and at transfer. Similarly, the final Emin is higher of the two values calculated at service and at transfer. Thus, we are having two sets of calculations, one for the service loads and another for the transfer. The values are selected judiciously, that for Emax we have two values, one for service, one for transfer. Whichever is lower will satisfy both of them, and that is selected as the final Emax. Similarly, we have two values of Emin, one for service, one for transfer. Whichever is higher of these two, that location will satisfy the strength condition both at transfer and at service, and we select that as the Emin. The expressions of Emax and Emin for simply supported beam were developed for positive moments. For a cantilever corresponding to a negative moment, the eccentricity implies that the CGS is located above CGC. Thus, when we are using the expressions from the simply supported beam, we have to be careful that the sign of the moment may be opposite, and in that case eccentricity refers to the location of CGS which is above CGC. To recapitulate the equations, for a type 1 section at service, we have Emax equal to M minimum divided by PE plus KB. This is the expression we have got from a simply supported beam, where we have substituted M min in place of MSW, and E min is equal to M max divided by PE minus KT. Both this Emax and Emin are being calculated at service, and hence we have PE, the effective pre-stress for both the expressions. At transfer, we have another set of equations where they are given based on the self-weight moment MSW and the pre-stress at transfer, which is P0. Emax is equal to MSW divided by P0 plus KB. Emin is equal to MSW divided by P0 minus KT. Again, these are the expressions which are similar to that of a simply supported beam, but we are applying both the expressions for transfer, and that is why we have MSW and P0 in both the expressions. Thus, we have two expressions of Emin, one for service and one for transfer. Similarly, we have two expressions for Emax, one for service and one for transfer, and from this we finally calculate the Emax and Emin at a particular location of a cantilever beam. This is the way we determine the limiting zone for a cantilever beam. For a type 2 section, we have Emax equal to M minimum at service plus FCT allowable times A times KB whole divided by PE plus KB. Emin is equal to M max minus FCT allowable times A times KT divided by PE plus KT. Again, note that both Emax and Emin are calculated at transfer corresponding to the minimum moment and the maximum moment respectively, and using the effective pre-stress PE. Similarly, at transfer we have two expressions of Emax and Emin. which uses the self-weight moment MSW and the prestress at transfer P0. Emax is equal to MSW plus FCT allowable times A times KB whole divided by P0 plus KB. Emin is equal to MSW minus FCT allowable times A times KT whole divided by P0 minus KT. Once we have these expressions of Emax and Emin, we can determine the limiting zone for a type 2 sections. For a type 3 sections, the expressions are same. The only difference is that we have different values of the allowable tensile stress at transfer and at service. Next, we are moving on to have an idea about the cable profile in a cantilever beam. The cable profiles for a few beams with cantilever spans are shown schematically in the following figures. The vertical scale is enlarged to show the location of the CGS with respect to the CGC. In these figures, we have enlarged the vertical scale to have a feel of the cable profile. The top one is a beam with a single cantilever, and you observe that in the backspan region, since it is subjected to a positive moment, we have a cable profile which is going down the CGC. Near the support, we always have a negative moment and hence the CGS is going above CGC, and in the cantilever part the moment is always negative and hence the CGS is always above CGC. Note that the cable profile which can be selected from the limiting zone has a variation which is similar to the moment diagram. The difference is near the support region. Since in a cable we cannot have a sharp kink, we are providing an intermediate curve at the support region without the kink. If we have a varying cross section in the cantilever span, we can change the location of the CGS within the limiting zone such that we have minimum bend along the length of the beam. This helps us in placing the tendon easily, and it reduces the friction losses in a post-tension beam. Thus, the straight profile of the tendon can be selected from the limiting zone, and the straight profile has less friction losses and it is easy to place before the post-tensioning operation. For a prismatic beam with uniform cross section along the length, the cable profile is similar to the moment diagram under uniform load. Thus, for regions of negative moment, the CGS is located above the CGC. Since there cannot be a sharp kink in the tendons and the supports are not true point supports, the profile is shown curved at the right support. For a beam with varying depth, the cable profile can be adjusted within Emax and Emin to be straight for convenience of layout of the tendons. For beams with double cantilever spans, again for a uniform cross section, we observe that the cable profile mimics the moment diagram where the CGS is below the CGC in the positive moment regions of the middle span, and as we go close to the supports, the CGS is above CGC in the regions where the moment is negative. In the cantilever spans, the CGS is always above the CGC because the cantilevers are always subjected to a negative moment. If the depth of the beam is varied, then we can select a cable profile within the limiting zone which is convenient to place and has less losses due to friction. In this beam with double cantilevers, a straight tendon can be selected. In fact, the straight tendon will be located above the CGC near the supports, and it will come beneath the CGC near the middle of the midspan, and the selection of a straight cable is more for convenience and to reduce the friction losses in the post-tensioning operation. Sometimes we may observe that the top of the beam is varying in the elevation, and for a beam with varying level of top of the beam, the cable profile can be selected somewhat like this, where the CGS is above the CGC in the cantilever portions, and in the central region the CGS is located based on the limiting zone. We are trying to avoid sharp variations in curvature so as to minimize the losses due to friction. Thus, the selection of a cable profile is dependent on the limiting zone that we have determined and also on the placement of the tendons and friction losses. A cable profile is selected such that the tendon can be laid conveniently and there will be minimal friction losses during the post-tensioning operation. In today's lecture, we covered the analysis and design of cantilever beams. First, we observed the different types of cantilevers that can occur. In a building, the cantilever can be a part of a continuous beam, but the cantilever extends outside the last support. If there is not a continuous beam, usually a cantilever is provided with a backspan to reduce the torsion in the supporting column. In bridges, there can be cantilevers in a balanced cantilever type of construction. That means over a pier, two cantilevers are progressively projecting out during the construction. There can be cantilever spans with an intermediate span in between. The analysis of a cantilever beam has to be done carefully by proper placement of the live load. As compared to a simply supported beam, the main difference of a cantilever beam is that under different positioning of the live load, one particular section can have either a positive moment or a negative moment. If we place the live load in the cantilever span, we get a certain moment diagram. If we place the live load in the back span, we get another moment diagram. If we have live load throughout, then it is a third type of moment diagram. From these conditions, we determine the envelope moment diagrams, which gives us a maximum value M max and a minimum value M min. These values are algebraic in sense. That means the M max has it can have a positive value or it can have the least negative value, and M min can have a least positive value, but it has the highest negative value. Now, once we have done the analysis properly with the different positionings of the live load, we have the design moments M max, M min for the design of a section of the cantilever. For the placement of the tendons, we use the concept of limiting zone. Now, first we revised the expressions of the limiting zone for a simply supported beam. What we have found that the maximum eccentricity corresponds to the minimum moment at transfer, and the minimum eccentricity corresponds to the maximum moment under service loads. These are for a simply supported beam. For a cantilever beam, the minimum moment need not be at transfer. We have extra moment conditions. We have one condition at transfer where the moment is due to the self weight, and then under service we have two values of moments M max and M min for a particular section, which are available from the envelope moment diagrams. Thus, to determine the limiting zone, we first use the M max and M min values at service, from which we determine one set of E max and E min. Then we again calculate E max and E min for transfer, and then we pick up the values of E max and E min which satisfies the stress conditions both for transfer and for service. The equations that we have written were for type 1 member and type 2 members. The equations are similar. The equations for type 2 member are more generic, because if we substitute the allowable tensile stress to be 0, then we get back the equations for type 1 member. For type 3 member, the expressions are same as that for type 2 member, provided we substitute the appropriate value of the allowable tensile stress. Now, after we revised the expressions for a simply supported beam, we got the expressions for a cantilever, which is the same expressions, but now for service loads we are calculating E max and E min corresponding to M minimum and M maximum respectively. Then at transfer we are calculating another set of E max and E min corresponding to MSW. Thus, once we have these two values of both of E max and E min, we finally come to the values of E max and E min which satisfies the stress condition both at transfer and at service. Once the limiting zone has been determined, we select the cable profile. The cable profile can be different type depending on the situation. If we have small beams with uniform cross section, then the cable profile mimics the moment diagram, where the CGS lies below the CGC in the positive moment regions and the CGS lies above CGC in the negative moment regions. Near the supports, the cable profile deviates from the moment diagram because we cannot provide a sharp kink near the supports, and also the supports are not true point supports. If the depth of the beam is varying for large construction, then the profile is adjusted within the limiting zone such that it is convenient to place the tendons, and we have reduced friction losses during the post tensioning operation. We can try to have a straight cable profile within the limiting zone, which will be convenient to place the tendon and will have minimal friction effects. We have seen the cable profiles for beams with a single cantilever, and also we have seen the cable profiles for beams with two cantilevers on the two sides. In our next class, we shall move on to the discussion of a continuous beam, which is an extension of the concept of a cantilever beam, but there the number of spans is more than 2 or 3, and we shall observe that the cable profile is similar to what we have seen for cantilever beams. Thank you.